Okay, students, let's do a short tutorial on Chapter 2. The first question, we are asked to find the determinant of D using only column operations. Only column operations. Okay, so we are asked to compute the determinant of D using only column operations. So you were given the matrix D, and it's the matrix 2, 0, 1, 1, 2, 0, 4, minus 1, minus 1. Okay, now we can go from D to a matrix D1 by doing something to D. And I'm only allowed to manipulate the columns because that's what the question asks. So I'm going to take minus half times column 1, and I'm going to add that to column 3. Okay, and so that's going to create the matrix D1. Okay, and then I'm going to construct the matrix D2 by doing something to D1, and I'm going to take a quarter of column 2 and I'm going to add that to column 3, and that's going to give me the matrix 2, 0, 0, 1, 2, 0, 4, minus 1, minus 13 over 4. Okay, and observe that the determinant of D2 is going to be equal to the determinant of D1, and that's going to be equal to the determinant of D. And why is that? Because remember the rule that we did in section 2.2 says that if you take a multiple of one column and you add it to another column, then the determinant of the new matrix is still the same as the determinant of the old matrix. Okay, so basically, knowing that, we said the determinant of D2, now D2 is a lower triangular matrix, so the determinant is the product of the entries on the diagonal, so it's going to be 2 times 2 times minus 13 minus 13 over 4, which is going to be minus 13. Alright, so the determinant of D2 is going to be the determinant of D1 is going to be the determinant of D, which is going to be minus 13. Alright. We are asked in 1.2 to find the determinant of D using only row operations. Okay. Okay, so we're asked to find the determinant of D using only row operations. So we have our matrix D, and what we're going to do to D is we're going to take minus 2 of row 1 and we're going to add it to row 3. Okay, so that gives me the matrix D1, which is going to be 2, 0, 1, 1, 2, 0, 0, minus 1, minus 3. Then I'm going to take negative a half the first, well, not negative a half times the first row, and half times the first row, yes, it is going to be negative a half. So you're going to multiply the first row with negative a half, and you're going to add that to row 2. Okay, and that is going to give me a matrix D2, and D2 is going to be 2, 0, 1. It's going to be 0, 2, negative a half, and my last row is going to stay the same. Okay, then I'm going to perform another operation, and I'm going to take a half multiplied by row 2, and I'm going to add that to row 3. Okay, so having that, that will give me a matrix D3, and that's going to be the matrix 2, 0, 1, 0, 2 minus a half. Okay, and that is the last row is going to be 0, 0, minus 13 over 4. Okay, and remember what we said? Observe that we said the determinant of D3 is equal to the determinant of D2. And the reason we said that was because we obtained D3 from D2 by taking a multiple of one row and adding it to another. And by our previous determinant laws, the new matrix you get has the same determinant as the old matrix. And we got D2 from D1 by taking D1, taking a multiple of a row of D1 and adding it to another row. So the new matrix D2 is going to have exactly the same determinant as the old matrix, which is a D1. And again, the determinant of D is going to be exactly the same as the determinant of D1, because we said we constructed D1 from D by taking a multiple of a row of D and adding it to another. So the determinant stays the same. So that is therefore going to be the determinant of D3, which we said is 2 times 2 times minus 13 over 4, which is minus 13. Okay. Okay, now look at problem 1.3. You're asked to find the determinant of A given that sequence of row operations. And now we have to apply that identity in section 2.1 and 2.2. Okay, now they ask us, given that sequence of row operations, we need to find the determinant of the matrix A. Now you have to know your identities well. So observe that you have the following. You have that the determinant of B is equal to negative the determinant of A. And why is that? Because to get to go from A to B, you need to interchange the first and the third row of A. So interchanging two rows, the new matrix you get, the determinant of that matrix is negative the determinant of the old matrix. And to go from B to C, we need to take a multiple of one of the first row and add that to the second row. So therefore the determinant of C is equal to the determinant of B. Remember, it does nothing if you add a multiple of one row to another. And we have the last one. To go from C to D, you have to multiply C. You have to multiply the first row of C with a scalar 5, and therefore we know the determinant of the new matrix is the scalar times the determinant of the old matrix. So therefore the determinant of D is going to be the scalar, which in this case is 5, times the determinant of the old matrix, which is determinant of C. Okay? So, thus, we said the determinant of D is minus 13. The determinant of D is minus 13. Okay? And therefore, which implies that the determinant of C is going to be minus 13 over 5, because you solve for the determinant of C. Okay? Now, because the determinant of C is minus 13 over 5, it follows that hence the determinant of B, which we said is equal to the determinant of C, is going to be minus 13 over 5. Okay, so now you have an expression for the determinant of B. So therefore, we have that minus 13 over 5 is equal to the determinant of B, which is equal to negative the determinant of A, which implies that the determinant of A is going to be 13 over 5. All right. Okay, let's look at problem 2. You're given that matrix with unknown k, and you're asked the first one to find all values of k for which the matrix A cannot be written as a product of elementary matrices. Right, so we're asked to find all values of k for which A cannot be expressed as a product of elementary matrices. Okay, now we know A can only be expressed as a product of elementary matrices if A is invertible. So essentially we want to find the values of k that'll make the matrix A invertible. So we're going to start off by finding the determinant of A. So using the cofactor, expansion, along the, let's do the first row. So along the first row, we obtain the expression for the determinant. So the determinant of A is going to be the entry in the first row in the first column multiplied by its cofactor, plus the entry in the first row in the second column multiplied by its cofactor, plus the entry in the first row in the third column multiplied by its cofactor. So doing simplification, you eventually get to this cofactor expansion sum, and then working that out, you get 2 times minus 1, the sign, multiplied by the determinant of the 2 by 2 matrix, plus negative 1, the sign, okay, and that is that quantity there. Right, so when is this quantity going to be 0? That's the question. Right, so if it is the case, if A cannot be expressed as a product of elementary matrices then it is not invertible. Okay, and that is by the equivalence theorem. Remember, equivalence theorem says that a matrix A being invertible is equivalent to saying that it is a product of elementary matrices. So therefore, the only way this can happen is if the determinant of the matrix A is equal to 0, which we know we said that's 8 minus 8k. And that's 0 if and only if k is 1. Okay, so thus if k is 1, then A is not invertible. It's not invertible. Remember, as the determinant of A is 0. We said a matrix is not invertible if and only if its determinant is 0. Okay. So it follows that A is not expressible as a product of elementary matrices only when k is equal to 1. Okay. Okay, so for the second part, we need to find all values of k for which the homogeneous system AX equals B has exactly one solution for every 3 by 1 matrix. Okay, so for AX equals B, to have exactly one solution, for every vector B, we need A to be invertible. We need A to be invertible by the equivalence theorem. Okay, the only way this can happen, is if the determinant of A is not equal to 0. Alright, so hence the determinant of A, which we calculated as 8 minus 8k, is not allowed to be 1. Okay, so hence, or rather, thus, the value of k needs to be in the set of real numbers without 1. Okay. Okay, now let's look at problem 3. You're given a triangle that's constructed in that particular way with edges of length A, B, and C and angles gamma, beta, and alpha. Use Cramer's rule to find that expression for cos alpha. Okay, so you have the triangle. And you have the angles alpha, gamma, beta. You've got the edge with length B, you've got the edge with length A, and you've got the edge with length C. Okay, so what I'm going to do is I'm going to draw a line from that point, this point, and I'm going to drop it straight down to this horizontal line here, and I'm going to let it drop to 90 degrees there. And then I'm just going to divide C into two parts. I'm going to divide it into R1 and R2. Okay, and then it's easy to calculate because then we know that R1 over B is the cosine of alpha and we know that R2 over A is going to be the cosine of beta. Okay, and from there we can then go and solve for R1 as B times cos of alpha, and we can go and solve for R2 as A cos of beta. Okay, and then from there you can note that C is the line R1 plus the line R2, and that is going to be B times cos alpha plus A times cos beta. Now you can do the same for the edge A and for the edge B, and you can we can also solve. We can solve for A as C cos beta plus B cos gamma. And you can also solve for B by applying the exact same argument. C cos alpha plus A cos gamma. Okay. Okay, so we want to find an expression for cos alpha using Cramer's rule. So we start off by saying the following. So observe that the system of equations correspond to the following system. Okay, so there you've got your matrix B0C, AC0, 0BA. Okay, and then you've got your variables, your first variable being cos gamma. Okay, your second one is cos alpha, which is the one you want to solve, and your third one is cos beta. Alright, and that should be equal to ABC. Alright, so by Cramer's rule, we said that we can solve our variable cos alpha as the determinant of the matrix A2 divided by the determinant of A, right, where we said that A is now this matrix here, the B0C matrix, AC0, and 0BA. Okay? And the matrix A2 was said to be BAC, AB0, and 0CA. Okay, so expanding along the third row, we obtain. So recall your previous definition of your matrix A and A. Alright, so what is the determinant? The determinant of A2, remember, how do we get A2? We cancel the second row of A and we replace it with a vector ABC. So we're going to take the entry in the third row in the first column, and we're going to multiply that with the cofactor of that entry. We're going to take the entry in the third row and the second column. We're going to multiply that with a cofactor entry. And we're going to take entry in the third row and the third column and multiply it with its cofactor entry. And that is pretty much going to be C minus 1 multiplied by the determinant of this matrix, BCA0. Because remember, I'm cancelling the third row and the first column, and I work the determinant of that matrix out, and that is going to be A multiplied by BAAB. Okay, and determining the determinant, you get AC squared plus A times B squared minus A squared. Okay, so that's determinant of A2, and then the determinant of A, you can again expand across the third row. So again, your cofactor expansion looks like that, right? Plus A32, C32 plus A33, C33, and that is going to be minus B multiplied by the determinant of BC, A0, okay, plus A multiplied by the determinant of B0AC. Okay, so that is then equal to B minus AC plus ABC, and that becomes 2ABC. Alright, so then go back to your Cramer's rule formula. You can solve for the quantity cos alpha, which is your variable. It's the determinant of A2, which is AC squared plus A, B squared minus A squared. And that you're going to divide it by 2ABC, and that's going to become B squared plus C squared minus A squared, and that's going to be 2BC. Okay, so not terribly difficult, just a straightforward application of Cramer's rule. Okay, next up we're going to look at problem number 4. Let A be an n by n matrix with the property that the sum of the entries of each row is 0. Prove that the determinant of A is 0. Okay, now we're asked to show that if a matrix, square matrix, has the property that if you add the entries of each row, it adds up to 0. So for each row, if you add up all the entries, it's equal to 0. So you're asked to show the determinant of this matrix is 0. Now, what does it mean for a determinant of a matrix is to be 0? It means the matrix is not invertible. So if a matrix has a 0 determinant, it means it is not invertible, and vice versa. So so we're just going to define the matrix A as with these entries. A to n. Alright, the nth row. Okay. Plus A12. A21 plus A22. Okay, so there you've got your equations set up, and now what you're going to do is you're going to say the following, right? So we have that this set of equations that we set up previously. All right. Okay. That implies that you can write it. You can write it this way. You can write that as the matrix A11, A12, A1n. Okay, up until your last row, AN1 plus AN2 plus, oh sorry, that shouldn't be a plus, take that out, ANN, okay. You can write that sum on the left as this following system here, okay, equal to, alright, so that translates to the system, to that system, which is the same as this system here. A x bar equal to 0 bar. Okay, where we said where x bar is 1, 1, up until 1, okay, and 0 bar is this matrix here, okay. Right, now if you go back to this system here, now we said this system, this is a homogeneous linear system, and we said that a matrix is invertible if and only if this homogeneous linear system only has the trivial solution, meaning that the only values of x that are going to satisfy this system are values of x where each x in my vector x bar is 0. Now you can see here that this is an x where each value in my column matrix is not 0. So this will imply, so note that this system here has a non-trivial, it has a non-trivial solution. Okay, so thus, by the equivalence theorem, A is not invertible. All right, whence the determinant of A is equal to 0. Okay.